she flies well.
I don't know.
Well, I wouldn't want to.
Like, do that with your guys just to like, people in front of me, people inside, people in back. Sorry, first time buyer. We'll see. I can afford it.
Okay, so we try to finish Chapter-7 and then we will do the lab for the cases that I told you like Tuesday. It's good review for Chapter-5. So Chapter-5, 6, 7, 8 will be on the second exam. So Chapter-7 we studied the so-called quantum mechanics model for atoms. So we talk about those very strange needs of electrons and some of those other particles like atoms, neutrons, protons in the atom. So the best model so far for those kind of particles is using the quantum mechanics model. So I think we talk about some of those very strange behaviors. So like one behavior is the electrons indeterminacy or uncertainty. So I think one experiment that was first one type of experiment that was first performed in the 1930s was trying to like see those interference pattern of electron beams. And interference pattern, like this pattern, is the typical behavior of waves. So this behavior is a wave. And well, that's kind of very strange. How can like some of those electron really physical particles behave as waves? But they do exist as waves. And then obviously electron is still like a particle because you can use electron to like produce those TV televisions, the computer monitors, right? So electron really you can produce electron from some electron like resource and hitting on the screen, and you will see like those pictures of the television or the computers. So then you try to detect where the electron were passing through. If you have like these two like narrow slits, and you shooting one electron at one time, so you can see like electron will go through either the left side or the right side. And you can do that, you can detect that with a laser beam. So once you turn the electron resource on or the electron gone from the television or the computer monitors, those old ones are those computer monitors, those are just LCD or LED. So then you lost wave behavior. Right? So you lost the wave behavior that electron that show you. So these two behavior, the wave behavior and the particle behavior, complementary. So therefore, the Heisenberger he produced a proposed principle. He said you cannot simultaneously measure or calculate or predict the position and the speed of some of those small particles. Actually, this principle will apply to all the particles. That means you cannot predict even like precisely what is the position and the speed of like a ball or car or airplane. But if you use his formula, you will find out the uncertainty for some of those larger materials you usually see is negligible. Because that depends on the mass. If the mass for like a car or for a ball is so huge, and you divide by these numbers, that means pretty much it becomes zero. So that means you can. It's kind of to our proceeding, to our measurement, or our eye, or our like perspectives. So those you can measure the position x, which is represented by the x. You can measure the velocity or the speed represented by the v, both precisely. But this is not true if you like think about use the mass of electrons, and then the number here is a very small number, and your h is a very small number, so you get some very reasonable number, right? So then how can we really like describe electron? So we know those. You cannot determine, for example, the speed and the position precisely. The so-called indeterminacy. And because of that, even if you use like the traditional or the older, the traditional like that or the first mechanicals, the so-called Newtonian mechanicals. If you accept that the last, what we said in the last slide, that uncertainty principle, right? So even you think about it, you don't want to like come up with some new model. You still want to use that Newtonian model, Newton's model, and you still want to use Newton's model. Newton's model requires something, right? You need to tell me what is the position for the ball, what is the speed of the ball, right? And then you can, if somebody throws a ball at you, you look at that. What is the position now? What is the speed? You can predict him where it will land, and you can catch it. Now, because of that last slide, Heisenberg tells you cannot measure or predicting precisely at the same time the position and also the speed. So therefore, you cannot know like what is the speed, what is the position of the ball. If you know the position of the ball is there, you cannot know the speed. So therefore, what is required by the Newton's theory is cannot be given to you at the same time for those small particles like electron and atoms. So that's really make us think about we are really necessary to produce a new theory. So then those kind of ideas few scientists accumulate, and one scientist finally like a breakthrough, and Schrödinger he proposed an equation, and this equation how he produced is not really come from like just from his pure like imagination. He compared some of those something else from some other fields. So that's the way of science. Usually you can interdisciplinary, you can always borrow something from some other field. If you study chemistry, you can use some chemistry principle in biology and vice versa. So he studied some of those people. Some people made some of those transition between classical optics, the light, right? And then those quantum optics. So there are some of those transition between that, and he borrowed some idea. I cannot say borrow, that's probably a bad word, but just get some of those, get some of those inspirations. He proposed equation like those. So that equation, you don't have to worry about that equation in this chapter. Just know that equation is. Those are the, if you study a little bit about calculus, you know those are the so-called derivative calculus, right? Calculus means integration and derivative. So then you have those, and then you will see like in this one you have like the time t variable in it, and but sometimes you will see that you can just separate that t out and get some of those time independent, which means you think about your atom in those kind of states that really always in those kind of states will not depend on the time. Right. So a story about the Schrodinger equation. So now we were not, that were beyond the scope of this class. So we'll just know there is a Schrodinger equation, and then we'll just see the result. So the Schrodinger equation, you can solve it precisely for some very simple, program. Okay? The simple program you can solve the Schrodinger equation precisely, which means mathematically, without any approximation, is for the H atom. H atom or a hydrogen atom. A hydrogen atom has only one electron. One electron and one proton. So that makes the program much simpler. And then you can solve that analytically, algebra, mathematically, or find some of those solution. Okay? The solution we find out from the Schrodinger equation has some of those special names. We call them mathematical functions or wave functions. And usually, most of people in the chemistry class or physics class will use this Greek letter psi. Because that equation, as you see from the last slide, that equation itself has that imaginary number I in it, and I equals square root over 91. And that is impossible because in those impossible in the real number regime. Right, so square root over 4 equals 2. And why is that? Because 2 squared equals 4. Right? And you want to find the square root of 91, that means you want to find the two real numbers that multiply to themselves, that equals 91. There is no such number. Multiply gives you 91. So those are the so-called imaginary numbers. Right? And so then you put it into that equation. Obviously, the solution, this side, also has those guys in it. So you call that those kind of functions a wave function, and but it has some physical meaning if you square that, and mathematically, you square that. That means that becomes a real number. So psi squared is not an imaginary number anymore. So once you square that psi, the I disappears. But if you have I in it, you square this I, and you get 91. Right, so then that is very important to us because we know we'll see what it is standing for. So initially this quantum mechanics model, nobody is sure about what it really tell you, and then more and more scientists, so these scientists do that equation, and then another scientist, Bohr, he made a lot of proposals. He proposed, okay, if you square this side, this function, you get psi squared. He predicting, he proposed this psi squared tell you the probability of finding the electron at one spot. Okay? Because this psi, this function, in general, it will depend on these three coordinates, the Cartesian coordinates, x, y, and z. So if you tell me one number for x, one number for y, one number for z, and I can fix one point in the space. So this scientists propose, if you square this psi, you get this psi squared, and then this psi squared will representing the probability of finding electron at this x, y, z spot. Right. So that's is one like something we get from that equation. And there are some other things we get from the equation. There are two more things we get from the equation. And we also get this E. And then also those are the proposals. Then finally, well, later on we find out those are true. And we verify when they're true, that makes sense, with experimental result. So that's representing the probability that makes sense. Now that number E, we call that is the energy for this state. So whenever you have a psi, you will get an E. And sometimes you might have two psi have the same E, but for every psi, you will have an E. And then those scientists also propose, so those E is the energy for that orbital, the electron in. And if the electron in that orbital, and that orbital has energy E, then we will see that electron has that much energy. Right? So this is the second thing we get from the equation. So 1 we get this, and 2 we get E, and E become energy, and psi squared become the probability. And number 3 is those quantum numbers. So that is the one we are going to talk about a lot in this chapter. Quantum numbers N, L, and ML. So that's the 3 quantum number. Is the number 3 you get from that Schrodinger equation. Understand? Now let's talk about what are those quantum numbers. So energy and that psi, and the quantum numbers are the 3 solutions, 3 results you get from that equation. Now let's talk about the first in detail. What are those quantum numbers? And we'll talk about what are those wave function psi squared looks like. And we'll also talk about what are those energy, how can we use them, do some of those calculation, prediction, or explanation for the experimental result. Right. So the first quantum number from the Schrodinger equation, we have 3 of those numbers. And well, actually there are 4 quantum numbers. There are 4 quantum numbers, but 3 of them come from that equation. And so let's first talk about these 3 come from that equation. And these three numbers, let's talk about them in two aspects. One is talk about what are their interrelation, numerical interrelation. And then secondly, we'll talk about because they have those numerical interrelation, interconnected, and we talk about together. Okay? Maybe sometimes we will need all the 3, sometimes we will need only 2, or sometimes we only need 1, and see what they stand for, what they represent. Right. So probably before this slide, and let me talk about briefly about that numerical interrelation between the 3 quantum numbers. Right. So the first quantum number is n. We talk about those numerical relations. Therefore, we first see what are those allowed values. So the allowed value for n is 1, 2, 3, and so on. Okay? any number larger or equals than 1, any integer number larger or equals than 1 is a good number. Right? So 1, 2, 3, 4, 5, 6, 7, and so on. Right? So the second number is L. L has starting from 0. And then if you have the numbers, just increase 1 at one time, just use dot. Right? And here you get the upper limit is n minus 1. Right? So we call this is your upper limit, and this your lower limit. If you want to call that number for n, and this is also the lower limit. I can say no upper limit for n. Right? Now you can see the connections, right? Because what number you can have for L is depend on the n. Okay? Depend on the n. The next one is I think that's for use. The next one number is ML. Okay? So M subscript L is the number 3 number. It has the over limit. So this will be our lower limit. And again, I will use dot, including 0. So I will draw a line here. O is 0.
Doesn't include 0 or does?
Does. So I write all the number here. That means included. Right. So that's 0. I draw the line there because I don't want to get confused between O and 0.
Oh.
So I usually will write 0 by draw O and lines through that. So that means 0. Right? And so then this also dot and dot. What do we mean by the dot? By the dot means you increase the number by 1 integer. Okay? So here, if you start from 0, the next possible number depend on, obviously that depends on your upper limit. Okay? If your upper limit is also 0, then you finish. You only have 0. Right? And that is like the connections. So then what is your upper limit for the L depend on the n. Right? Seems that you are confusing, right? So what is the upper limit for you have n equals, you can have 1, that's okay. And 2 is okay, 3 is okay, and 4 is okay. Any other numbers? Now let's see the L. For each one set of number of n, let's find out what are the possible number for L. And because this L depends on the n. Right? So all the L, be starting from the lower limit. All the numbers were starting from the lower limit. Okay? Right. So you always has the 0 to starting from. And so that's the sort of this lower limit. Right? And the upper limit is n subtracting by 1. Okay? Now for this example, if your n equals 1, so what is your upper limit for L? 0, because n is 1, so 1 minus 1 is 0. Okay? So therefore you will have a 0, and then dot, 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 according to the formula there. Right? So this 0 come from, this 0 come from that 0. Right? This 0 come from n subtracting by 1, that's also 0, because you have n equal to 1. Understand? Obviously that doesn't mean to understand. You don't have to repeat in zeros, so therefore you don't have any charge, it just become only one number for this L. And this is only one combination. So that means if you tell me the n is 1, your error can only be 0. That doesn't mean error can always be like that. And that depends on this n. Okay? So for this n, then we talk about this quantum number we talk about in two senses. We first talk about what are those what value are allowed. Then we talk about they are together or by themselves, what they mean. Right? Yeah, question?
No.
Yeah, so there's only one number for L if your n is 1. That, as I said, that is only one. These two together like this. Okay? And obviously you can have n equal to 2. Right? If you are n equal to 2, so your error, again, you will start from 0. Right? And usually you can specify the upper limit. So what will be our upper limit for this? If we have n equal to 2? Or 1, because n is 2, so 2 minus 1 is 1. So that's your lower limit, that's your upper limit. What this data means is some number, some of those integers in between this lower and upper limit. So if your upper limit is 1, lower limit is 0, there's nothing in between. Just go from 0, adding on 1, you get 1. Alright, very good. So then what will be the possible value or possible number for error if n is 3? You're starting from what? So the first number is possible is 0, the lower limit. What will be our upper limit? 2. Okay. Yeah. So that will be 2. So 3 is n. Okay. So 3 minus 1 is 2. This comes from n minus 1. n minus 1 becomes 3 minus 1. For different number of n, you will have different number for n. You put whatever number for n and do calculation. And obviously there's some number in between this 0 and 2. Right? What are those integers? So we talk about those integers in between. Right? You add in 1 at one time. You take 0 plus 1, you get 1. You take 1 plus 1, you get 2. Therefore, you have only these 3 numbers. Right? Right. So now, what will be the possible number for L if our n is 4? It will be 0. Our upper limit will be what? 3. If you take 0 plus 1, you get 1. You get 1 plus 2, 1 plus 1, you get 2. 2 plus 1 is 3. So therefore, we have all these 4 numbers. Right, no, because the number for n and the number for L sometimes they're similar, they're kind of confusing. You see that L is 1, there's 0, and when L goes to 2, there's 1 here, there's 1 there. I think that's one reason we said to get rid of the confusion, and you will send a letter for those numbers for L. You can have L 0 here, and you can have another 0 here for L. Have another 0 here, and another 0 here. So no matter where you get a 0, you get a 0 from 4, from 3, from 2, from 1, and you just use a letter S. And which is very important for this traveler and next traveler, because you will see those sort of the electrons, they exist, and this shell, and shell, and shell. So for every those numbers that are given by n, you call them all those side squared. We call them orbitals. And you will see like in details about those, but for right now we will see we have all those electrons in those guys, and those guys we call them orbitals. The orbital, we organize them. Okay? We say if they have the same n, and we call them in the same shell. Okay? If we find out on the side, and all the side has have the same n equal 1, because this is your first shell. And you find out on the side that in second shell, or have that n equal to 2 in the second shell. Right? Right. Now let's go back to the problem about those number relation between those quantum numbers. We already find out n can have 1, 2, 3, 4, 5, 6, 7, and L can only from 0 to n minus 1. So we have this kind of 2 examples. Continue with that, yes, to get less confusion. So every those number that for L is 0, you just call them S. But then you see what is the difference between this S here, right? And this is S here, and this S here. Right? By convention, everybody agrees. So if you find out your L is 0, you just can call that 0. You can just call that S. You can tell me L equals 0, or you can see just S. You see S in this section, I know your L is 0. So now how you tell the difference between this S, and this S, that S? So by the way, those S or those signs represented by this L itself, we call them subshells. The subshell is related, in one way, related to the L. The shell only depend on the n. That's you need like a few just hang on that. So the subshell depend on the L. Because you already see that, you can see that there's 0 here from this 4. You have this 0 here from this 3. And this 0 here from 2. This S here from 2. This S from 1. And obviously, all of them, we call them S, and there's no difference because this S comes from 4. That comes from 3. So to make them a little more clear, just adding those numbers, and so this become 4S. This become 3S. This become 2S. That become 1S. And so then now this will be completely understandable. That means 4S together precisely is what's subshell. Well, you can also think about those L by themselves tell you the type, tell you whether you have S type, P type. So this will be the P type, and this will be the D type, and then the other one, the last one, the F type. So by the L itself, it can only tell you the type. Do you have the S type? Do you have the P type, the D type, or the F type? Okay? And you want to be more precise, you see like you get the S type. Okay? And you can precisely tell me what S. You can see 4S, 3S, and 2S, 1S. Right? And so this same, so no matter where you get the 1, so that will be P. No matter where you get the 2, it will be D. And then no matter where you get a 1, you get a P. Right? So you can see first, once you identify the L is 1, you know that the P orbital. And again, you want to be precise, so this will be our 2P. And this will be our 3P. Right? And this will be our 4P. And then what about the D? D is similar. Right? Whenever you see D, if you tell me you have a D type of those subshells, I know your L is 2. And you can tell me where you get the 2. And obviously you can get a 2 for this number from 4, so you have 4D. right? And that you can get from 3 to get 3D. Oh, we have like a 2D? No. Why we don't have a 2D here? Why we don't have a 2D? D, which means what is the number for D? What is the number for L? It's 2, right? We did not have a 2 for this shell, for this level, and sometimes shell also called level. I mean, you have the stair, one level, not level. So the shell also called level. For this level, and because n is 2, right? N is 2, you cannot have this L is 2. Why you cannot have L is 2? Because our limit n minus 1, and this you're kind of going back and forth. You think about what are the sort of the numerical interrelation between those numbers. Okay? So if you specify those shell or level, that means you tell me what is your n. Once you have the n, you have the upper limit for L. So therefore, we don't have a 2D. Similarly, you don't have 1P, 1D. Forget about 1D. You don't have even 1P. Right? In order to get this 1P, that means you have to have you need to have a 1 here for L. Do you think it's possible to have a 1 for L if you have n equal to 1? No, your upper limit is 0. Right. So then similarly, this F will be our 4F. I was thinking about to tell you this numerical relationship and what this standing for separately. But when I talk, I will tell them at the same time. As I tell you the relation n equals 1, 2, 3. Then L is 0 and n minus 1. So that's, they always, once you understand the numerical relation, you understand what they're standing for. Right? So n by themselves again is the shell or level, and n and L together is the subshell. Right? Well, now where are the electrons? So electrons in those. Electrons in those size first. In the sort of orbitals. And then you sometimes want to understand, try to wondering, right? So shell obviously is a shell. So like you can see, this is a shell. So inside there may be like only one something, or maybe many something, right? So once you organize those orbitals into shell or subshells, the subshell, so those subshells S and P, SPP and SPPF, those are all subshells, might have a different number of orbitals, and that's the reason we have the next quantum number. Next quantum number, so let me write it here. Next quantum number, I'm going to finish writing. Next quantum number is ML. ML you go from negative L, and then you go to 0, then dot, then you go to positive L. I think I went that away because we think about what I mean by the dot, right? Right? So I think now you understand what I mean by the dot, right? Right? So let's go back to this picture here. And if you have that n equal 1, your L is 0, so according to what we write here, your ML can have the value from negative L, and also including 0, then go to positive L. Alright, so then for this possible number, you only have one number for ML. Understand? Why is that? Because here, here you have one number for L. The number you have for L is 0. If you put into that formula, you get a negative 0. Understand? So the formula tells you start from negative L. If your L is 0, you have negative 0. You're always including 0. So 0, 0, then you have positive 0. And obviously there's only one 0. No matter if positive or negative 0, you just have 0. Understand? So therefore there's only one number for ML if your L is 0. Right? So that's similar for here. So now we have to make here we'll make like another small line here. Right? Right? So for this L is 0, what will be the number for ML again? Only one possible number is 0. Now you tell me what will be the possible number if your L is 1. If your L is 1, then what are the possible numbers for ML? Will be negative 1, starting from negative 1. Right? Starting from negative 1. Right? Now those dots, what we mean by the dot is any 1. Right? Right? So negative 1 plus 1 is what? 0. 0 plus 1? 1. And this will be our limit. Alright. So then let's see, this will be similar for this. Probably will be out of space. Right. What are the possible numbers for 3s for the ML? 0. What are the possible numbers for 3p for ML? Negative 1, 0, and 1. What will be the possible number for ML if you have the 3D? Very good, very good. This is negative 2, negative 1, and 0, and 0, then what? Any.
Plus 1, plus 2.
Positive 1, then any, positive 2. And you stop at the 2 because what? You stop at 2 because what? So this is our limit for ML. Alright, so I will skip a few here because you already found out what's the number for S. Right? S means L is 0. If L is 0, then the ML can only be 0. You already know P, and no matter 3P or 4P. If it's P, that means L is 1. If L is 1, then ML negative 1, 0 plus 1. You already know what is D. D means L is 2. If L is 2, then ML is negative 2. Let's see here. Negative 1, 0 plus 1, and plus 2. Right? Very similar. So if you see F, 4F, you cannot have 3F. Similar reason, you cannot have 3F. If you have 4F, that means your L is 3. Right? If your L is 3, then what is your number for ML? Negative 3, negative 2, negative 1, 0, 1, 2, and 3. Yeah. Very good. So then, what do we mean by that? Why we only have one number for the S, for ML? We only have one number for S, for 2S for ML, and a 3 number for ML for the D. Agree?
Because they have different shapes.
Those are very good. So those are different shapes, actually. So those are different shapes. So we have those. We talk about those S means the spherical. P, so S is spherical, and P are those kind of dumbbell. You guys work out in the gym. Dumbbells. And then D like you have 5 of those. 4 of them has those kind of shape. And another one has those kind of shape. Alright. Alright, so this is S, and this is P, and this is D. Or I cannot see the I think that's the F type. But it's getting more and more complicated. So I think those number is tell you how many you have. I mean the number for the ML tell you how many you have. Right? See the shape for the spherical? How many possible shapes you can have for spherical? I mean just roughly just you have the spherical like spherical, just one spherical. Right? Right? So therefore there's only one of those S orbitals. But there's only one number for ML. Okay? So no matter what S orbital you have, you know there's only one S. In that sense, right? And so that's why something computing. Obviously you have one of those one S. And you will have one, two S. For each S type, there's only one orbital. Does that make sense now? Alright. So then, how many number or how many values we have for the ML for those P type? 3. That 3 tell you you will have 3 of those orbitals. Okay? Because the 3 has different orientation. Okay? Let's say this is a, so this is a, so let's say this is a p orbital. Right? So this is a p orbital, like the 2 dumbbell, right? And you can have this orientation. You can, this is p orbital. And your p orbital can line like this. Or you can just stand up like that. Or you can do it that way. Right, so those orientations. So therefore you have 3 of the p orbitals. So no matter what p, you have 2p, 3 of those. To make us easy to understand, you can just say you have a 2px, and you have a 2py, and you have a 2pz, x, y, z.
So you count the 1, 2b, and the other, the 3 numbers as 1, so, or the last 3 numbers as 3.
Yeah, the last one number, ML. If the ML has only one number,
So that's 1 of it.
one orbital, for one orbital. So how many orbital? What is orbital? Orbital is where it's kind of like the container. Is the bucket or the box or the room for the, so that's for the electron. So where the electron reside, the electron exists in those orbitals. Okay? And that is much complicated than like the Bose model, right? Bose tell you where the electron. Bose will tell you the electrons go like this. Bose usually seeing electron is a wave. But his wave is very simple. So he said electron is a wave just like those, they just travel like a wave. And in the same time they are like a wave, they will in the same time they also travel in a circle. So that's Bose model is kind of classical, a little bit like those ideas, the quantum models in it. Now we said a totally quantum mechanics model. So the orbital becomes those kind of shape. Okay? So this is spherical, and you can think about this shape like that. And I draw that little synchrite, see that you have this sharp cutting line, so the line like this. And then you think you get some impression, the electron can only inside here, cannot be outside here. But electron, just those are probabilities, density, possibilities. So we usually, when we draw something like that, it means you have 90% of probability finding electron in there. There's still 10% outside. Alright, so now you find out the pattern, right? How many, so therefore, how many, like, if you summarize, how many s orbitals do we have? So we have these 4 different types. There are more types. You usually don't use those. You have S type, P type, and D type, and F type. And what, or we call them, so those are the subshells. The subshells. You agree? Okay. So those are the shells. Those are subshells. You can put a number in there. Right? You can put a number like 4S, 4P, 4D. But usually, if I don't put a number, I only just concentrate on those types. Okay. So this type of subshell called F subshell. This is called D, and they're called P, they're called S. Okay. From this picture, you can summarize how many orbitals, number of orbitals. Right. So you can tell me how many orbitals are already in the S? How many down? Why there's only one? There's only one number for that there. Okay. How many orbitals for those P type? Do you remember? 3. Okay. Why there are 3? Similar reason. How many number for the ML? 1, 2, 3 number for the ML. Okay. Now you find the pattern, right? So now you find the pattern. How many orbitals for the D type? 5. Why 5? See here, right? 1, I mean 1 number, -2. 1, 2, 3, 4, 5, 5 numbers. Where did you find number? From the 2. What are 2 standing for? This means L is 2. And that's very similar here. It's kind of confusing, just like you study organic chemistry. So it's a lot of those simple problems. You have just try to put them together. Alright, so now how many F orbitals we can have? 7? Why 7? See the 7 number here? See the 7 number here? You start from -3, -2, -1. Alright, so in general, for some other L, so if I erase this, so again this, if we put dot, there's some other type. If you study those high energy physicals, so our F is G, and all the other will alphabetic order. So F and G, H, I, and so on. You can name all those numbers for L with those letters. Right? So if I draw all those dots, it means I will have just a number L. Right? Now you find another pattern. So what will be the general formula to calculating how many orbitals if we have L? 2L plus 1. See here? This exciting gas, this L comes from here, from where are you? This comes from this F, right? F means L is 3. So you take 3 times 2 plus 1 and you get 7. Right? Understand? Right? So according to this scheme, the next one is G. So G will have, what is L for G? L will equal to what? We use this for common, S, P, D, F. The next one will alphabetic order. F, G, H, I.
-4.
Very good. So that means your L is 4. L is 4. And then for those, let's say those You add the 4, you cannot get the 4 here from this 4. This is n, right? So let's finish this one. So this for this, this for this, this for this shell. So next one will be your number 5 for n. Then you will have all those. But once you have the 4, come from this 5 for L, and then you will have the -4, as you said, right? -3, and then you get a positive 4. And obviously you figure that out is how many. Use the same formula, right? So if your L is 5, and your L is 4, right? Add the 4. So n is 5. Right. So that's how many you have? So in general, this is L. This is general formula. If I write it here, so I don't use dot. Right? Next one is okay. So anyhow, I think that's done really something. So that's just remember that this first 4 type. Okay? That's the first 4 type is S, P, D, F, and those G, H, I, you don't use them. Alright, so we finished this first concept. I think in the same time I also give those connection between them, and together they specify those orbitals and so on. Right? Right. Now, individually, sometimes you can also see what it means, and a lot of time you have to figure out what they're standing for by connecting them all together. Right. So this just, I think this review what I just said. And so the first number is also the principal quantum number n, and you can have any number larger or equal to 1. I give you them with detailed numbers. It means 1. It means 1, and so on. So n can be any number larger or equals than 1. And then the larger the n, the more entry it has. Remember I talked about you get 3 things from that equation. Okay? You get the psi, which are the orbitals. So those are the orbitals. And you also get the energy. And then you also get that these 3 quantum numbers, N, L, and L. So in terms of energy, the larger the N, the more energy the orbital has. And the energy are defined as negative. So more energy, that means it becomes literally less negative, closer to 0. And also as the N getting larger, okay, so because n, I mean those quantum number, the energy orbital are all come from that equation, so therefore they are also all connected. So when the n getting larger, the orbital getting larger. And what that means, you have those S-type spherical shape, the P-type, the dumbbell shape, and what the difference between them? You have the 1S. Has the lowest energy, it's kind of like deep in the bottom of a well. So it's deep into a hole. Right? So that's called the 1S, the lowest one. And then you have the 2S. will become a little bigger, and the energy goes a little higher. And also tell you as the n getting larger and larger, so those energy getting closer and closer. Questions? What? Yeah. Question? Okay. So this last one, that means, let's say this energy here. So this is the energy increases going up. I draw a line here. That means this lowest energy for n is 1, and then the next one will be n is 2. It's a very rough approximation. Okay? I think that means all those, when you draw that 1, there's only one orbital, that 1s. When you draw 2, when here 2, but this line representing there are different orbital in it. You have those 2s2p. So 2s2p, they might have different energies. But in the simple problem, like for the H atom, 2p have the same energy, so therefore I just draw one line for n is 2. Just show you this idea, what we mean by that. Okay? So if you draw another line, n is 3. I only have one line here, that means there's only one level for the energy for all those guys in 3. If you have an n is 3 from this picture, you can see you can have a 3s, 3p, 3d. And 3s, 3p, 3d, in general, they have a different energy. Right? But just get an idea, talk about this n, and we can just think about the H atom. So for the H atom, 3s, 3p, 3d, they all have the same energy, even though they have a different shape, they have different size. So I draw like that. Right? And if you have that 4, you will have that n is 4. See, this picture tell you, so the line getting closer and closer. Okay? That means as n getting larger and larger, the line getting closer and closer. Why bother to show you like on the last slide? So this is like the energy level for the hardened atom. Again, for the hardened atom. So therefore, you don't have those details. You don't have the details. You just have one line here for n2, one line here for n3, one line here for n4. That is under this assumption for H. For H, you don't have to tell the difference between S, P, D, S, P, D, F. They all have the same energy.
Can I ask you a quick question?
Yeah.
In relation to the hydrogen atom, or just any atom, like where did you come up with the N from?
The N is for any atom.
Okay, they all.
So those
had
quantum numbers for
one
any
energy.
atom.
They all had.
Yeah, they all have those. They all have the N, L, ML,
Right.
and they have all those
But
energy.
like, how do you know how many N's an atom would have?
They have infinite. The
Oh,
N.
okay, they're just showing you the first
Yeah,
one.
yeah,
Okay.
yeah. Usually you just see the first few.
Okay.
Alright, so that N just, if you talk about N by itself, and you obviously N, you talk about the electrons, and obviously electrons depend on also the L and ML. So we try to make the problem talk here a little simple, and we say that for the H atom. For the H atom, so again, those different, in terms of energy, these still have those different shapes. So for the H atom, the 3s, 3p, 3d all have the same energy. Understand? So let's say for any atom, you will have this 1s. And for any atom, you will have 2s and 2p. For any atom, you have 3s and 3p and 3d. And 4s, 4p, 4d, and for F. Only for the hardened atom or the H-like. So the book will tell you H-like. Which means usually you don't worry about how many proton in the center in the nuclear. Just worry about how many electrons. If you only have one electron, and so if you have those helium, 1 plus ion, and also it will also follow those patterns. Because because helium like number 2, that means you have 2 electrons. If you have plus ion, that means you lost 1 electron. Understand? If you lost 1 electron, so the helium ion becomes also only 1 electron. For any 1 electron problem, H atom or the helium ion, and they all have the same pattern for the energy, so energy will not split. So you have a 1, there's obviously don't need to split, there's only 1 orbital for the N1. For N2 you will have 2s2p. Okay, then go back to this equation. So this equation you use that a lot in this chapter and in this class. And you get this equation from both this model, the simple model, and also from the new model, the quantum model. So you can see in this equation, this n, the En only depends on this n. There is no L, no ML. So therefore this equation is only precise for the H-like atom. So we talk about this quantum number L. You all know what value you can have. You can only have from 0 to n minus 1. And you also know for each one number for the L there is a particular letter. So L0 is S. That's what S. That is what is S orbital looks like. S orbital looks like a spherical. And this is where the electron is. Most of the time. Okay? Because this is 90% of the time you need. So you remember L is 1 is P, the sort of P. The shape of P are those orbitals. This picture is a better picture because I show you in both ways. So this is really reality. You see the dot? There's more dots near the axis, gradually smear out. The dot density, how many dots you have, representing the probability. More dots, higher probability. Right? Obviously, not a convenience. Why you draw so many dots? What you draw, just draw a specific shape. And this specific shape doesn't mean you're cutting out all the possibility of the electrons beyond that. So what is the letter you use for L is 2? D. Right? So I think that's here. Right? For L3 is what? Remember? Right? F, right? And this is D. And this is F. Now why have those? So then you say how many orbitals in those for those S type or the S subshell? How many orbitals for the p subshells? That depends on what? That depends on what again? Depends on ML, right? Depends on how many ML you have. So you can hear you already know the number can only have go from negative L to positive L. You also know this ML specified orientations, this way, that way, or 4, and 5, and so on. Right. So you also the value and the value of ML also give you the number of orbitals of a particular shape. Understand? But this is ML depends on L for a particular shape. Particular shape will depend on L. Okay? So if you have L is 0, you have S, and you have only one number for ML. So therefore only one orbital. Okay. I think don't push yourself too hard. There's so many information in like one class. It's very difficult to in your mind right now to summarize all those information. So for L equal to 2, what it means is our D type. Understand? L is 2, particular shape. So L is 2 is what a shape? It is a D shape. L is 1 is what a shape? P shape. See here? Right? L is 0 is what a shape? S shape. Right? L 3 is what a shape? F shape. Right? Right? So you have those ML numbers. If I tell you L is 2, and your ML is from this formula, negative L to positive L. If your L is 2, therefore you sign from negative 2, negative 1, 0, positive 1, and all together, 1 number, 2 number, 3 number, 4 number, 5 number. 5 number, that means you have 5 orbitals. And so then to really describe the orbitals, you need all the 3 numbers. But you have a different level of organized. If you only tell me like the number n, then you only know what are the principal level. So then I go here, the level, or the shell. If you tell me 2 numbers, you tell me both N and L, so then you tell me the subshell. And you precisely tell me, do we have a 3S? Do we have a 4D? Something like that. If you tell me all the 3 numbers, you tell me like the N, L, and also ML, and you tell me precisely 1 orbital. Right, so vice versa. If you tell me like 1, if you said you have 1 orbital, right, and we can figure out precisely that is 3 quantum number. So those orbitals and quantum number is similar as what I organized here. Right? Is organized here. If you look at this, this N, okay? So this N. And here we have 3 examples for N. So we have 1, 2, and 3. That's 3 numbers for N. If you only tell me that, and I only know that the so-called the principal level. So I said the first level, the principal sometimes you don't have the negative side. You will see just first level, second level, and third level. And if you also want to go one more step, and if you tell me that N is 1, if you still remember those formula for the L and for the ML, you figure out there's only 1 possible number for L. If you have N is 1, there's only 0. So very similar to what we have here, right? So therefore, for this first level, there's only 1 sub-level. So there's 1 sub-level here, only 1 sub-level. And for this second level here, you have two S sublevel and two P sublevels. So therefore, we have two sublevels. Okay? In order to get these two sublevels, you need two numbers. You need this N. You also need this L. But obviously, this L you can figure out by yourself if you remember that formula. And so this N3, that means your third level. If your third level, you can, if you tell me, if you don't want to bother, like I don't want to do the calculation to figure out what is the L, I just say N3, then I just say you have the third level. Okay? So I figure out in third level, how many sub-levels? Very easy, you see, what are the possible levels for L? L is from 0 to n minus 1, so therefore it's 0, 1, and 2. So you have 3 number for L, that means you have 3 sub-levels. So 3 S sub-level, 3 P sub-level, 3 D sub-levels. Right? Now you think about, yeah, I feel like pretty much energetic. I can figure out what is the ML. Then you think about the equation for ML, right? ML, see ML depends on the L, right? For L0 there is only one L, there's only one ML. For L is 1, you have 3 ML, that means you have -1, 0, +1. And these 3 numbers tell you we have 3 of those orbitals. And you have 5 number here, that means we have 5 of those orbitals.
So are these orbitals like where the electrons are?
Yes? Yeah.
So does it matter though? Like, I feel like it should matter as far as, I mean, like you're gonna have the same number of orbitals and then only have 1 electron as opposed to an atom that has like 20 electrons?
Yeah, they are different. Yeah, but in general, they have the same name. Yeah. We only find out precisely for the H atom, 1 electron, 1 proton.
Is all we have to care about?
All others, you don't have those, really, you don't have those come from the mathematical equation.
Okay.
So we saw they are similar. They will have the similar shape and similar logic. But really, nobody really solve those equations. Get like mathematically get those like what is that? Well, for example, what is that? This 3s looks like for, let's say, for the lithium atom. You can figure out what that looks like precisely for the H atom. You have the mathematical equation. If you just increase to lithium or helium, like helium, what is 3s for helium looks like? You can only do the sort of simulation, use like those numerical calculations. There's a lot of those software you can calculate, you can buy, you can calculate. But those are not really from those mathematical equations. Alright, so what are the quantum numbers and names for example, when we talk about those S and P and D, 3S, 3P and 3D? For this N, the 4 principal level, what that means is you just list out N equals 4 here. Right? Then you list out what are the possible L, what are the possible ML, then you think about what are their names. The name will only depend on this first two. Okay, so the name will depend on the first two. You just call them like something like this. Is that the examples? Those are the names. You can do a very quick like practice, right? So if you have N to 4, what are the possible numbers for L? Again. 0. What else?
1, 2,
1,
2,
2,
3.
and 3. All of them, that means you have all of them I just write here, that means you all have this is 4. 4. And 4. And 4 here. Right? So when you have N4, N2, right? And these 4 numbers is all okay for L. Right? let's think about, so this title. What are the possible number for ML? If you, let's do one by one. Okay? So this, how many L we have? I draw that line but too long, but that's come across that, that's what it is. So I will draw something like this. So this is for this, and this is for this, and this is for this. You all have this, you all have that N4. Right? So when you have N4, you can have this 4 number for L. I think one thing you bring, you know for sure, is you cannot have a 4 here. But you probably what bothers you now is why you have all these 4 numbers in the same time. Yeah, that is the reality. Okay? So that means when you have those orbitals, okay, all those orbitals, they can have the same n, but they can have a different, they can have a different shape. So this one is not okay, right? So n, if you have n 4, L cannot be 4. So the largest L is always 1 less than your n. If you tell me your n is 5, you cannot have 5 for L. You can only have 4 or smaller. And don't bother, but you can have multiple. You can, if you tell me like I have n 4, I can have all these 4. It's okay for L. So then you just think about them like 1 pair at one time. Sometimes you think about all the 3 pairs at one time. Right? So then once you can accept that, I think right now you just bother. You tell me that it seems like there's one-to-one connection. So if you said n 4, there's only be 1 L, that is good. If you're n 4, all these 0, 1, 2, 3 is good for L. So as long as you understand that, you go to the next step. You see what are the number of L. The L will depend on what? Depend on the ML. The ML will depend on L. The M, you go to the next one, the ML. ML will depend on the L. Right? Let's see the first one, so we'll think about the ML. You remember the ML, let's see that the formula is like, if I write here, the negative L, and 0, and then L. You understand? Right. So therefore, what would be the possible number for the ML if your L is 0? Only 0. Right? Now this one is okay, because that's kind of one-to-one connection. So you have 1 L and 1 ML. Right? Now the next one. Right? So the next one is is 1. So if your L is 1, then what are the possible number for the ML? Anyone, 0, and only 1. Now that's sometimes confusing again. So there's not a one-to-one connection, right? So 1 L give you 3 ml. There 1 L give only 1 ml. But that depends. That depends on what is your L. So you just have to accept that. I mean, if you tell me your n is 1, you only have 1 L. You only have 1 ml. Then everything is 1 and 1. So now let's go to the next one. If you tell me L is 2, so what are the number for ML? Negative 2, negative 1, 0, 1, 2. Similar, so this one is not allowed. So then you do that. Okay, so now we go on to this one, right? Because all of them have the same name. I think that will be clear, right? All of them have the same name. Now you have the L is 3. L is 3. And what are the possible number for ML? There you go, negative 3. Well, you know, negative 3, negative 2, and then what? So then what are the names? Yeah, that's very good. So S means L is 0. Yeah, very good. So this one, yeah, I know that right, you can write. So this one is name is what? For S. For S here. Right. Well, here you have how many orbitals for this 4, N4, and L1? That's 3 of that. That's 3 of that. Now you can tell the different, like what I did there, you can call them 4px, 4py. Otherwise, you just call them all 4p. So you just say here 4p. Understand? Or you can call 4px. Either I don't mind if you call them all them 4p. 4p, 4p, and 4p. Understand? Right? This is $100 of something. That's good. Right. Let me just get rid of that.
These are
So that is like the 3 something we get from the equation. Okay, so this is the 4s, right? Or is it just only one 4s? This is for what? 4p. Why I got the 3 4p's?
There's 3 different shapes up here, right?
The 3 4p's, so you have these 3 numbers here. Yeah, three different orientations. 3 different orientations. Right. So how many of that you have? Right? And this, how many of those you have will tell you how many orbitals. So that means we have 3 of those orbitals. What are the names for these 3 orbitals? All of them 4p. Right? So now, what do you call this? What do you call this? Those of you guys, like that N4L2. N4L2, what do you call that? 4D. And 4D. 4D. How many 4D do we have? Very good. Yeah, very good. How you get the 5? 1, 2, 3, 4, 5 numbers. Get it? You can call them all like 4D. Like you can call them 4DX, Y, 4DZ, Y, but I don't mind just calling them all 4Ds. Right? So we call them 4XY, that means they are in the XY plane as orientation. Understand? Alright, so the next one is this combination. So this combination here, 4 and 3. What do you call them? Well, first you figure out what number you have for ML. And you see how many of that. So what are the number for ML? If I have this L, right? -3, -2, -1, 0, 1, 2, and 3. Very good. Okay. Now you will give them a name. What are the names for them? Yeah, so they all 4F. 4F, 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 4F. I think there's one more 4F, right? 7 of them. So here, 5. And here it's 7. Alright. Now, once you find out how many for each subshell, for each of those types, for each of those shapes, okay? And you can add them together. All together, how many do we have? 7 plus 3 is 10, right? 10 plus 5, 15, 15 plus 1, 16. And there's also a formula that actually calculated. So this, how many orbitals? In N4, 16. How can I get 16 from 4? Square that. There's another pattern, okay? Those guys you call them what? Those right here, you have a name. What do you call them? Sub. Can you read that? You call sub. If you get confused, I don't complain about you confused, because there's some people call the sub-shells, some people call sub-levels, you just different shape. Alright, so for this shape, so for the dumbbell, there are 3, right? Another pattern I want you to find out is how many orbitals you can already find out for the given n. You just do what? Square the given n. If the given n is 4, you square 4, you get a 16. Right? So another question is how many sub-levels how many sub-levels? Sub-levels equal to how many? You find a pattern there. Same as n. See this here? If n is 1, there's only one sub-shell, it's 1s. If n is 2, how many sub-shells? 2 of that, right? 2 has 2d. If n is 3, how many sub-shells? 3. And now again, the question is about how many orbitals, how many sub-shells. Why you talk about those? Because orbital is where the electron in. Then you organize them. You kind of like, okay, so those guys, I call them have the same shape, and they have this, you call them sub-shell. Yeah.
Are we gonna have time for all 3 labs?
Which orbital is described by the following set of quantum numbers? You can find out when we see what this means. Which orbital? Okay. Which orbital? This question depend on the choice. If I give the choice like 1s, 2s, and those are the notation. So those are the notation for the sub-shell. For sub-shell. So therefore, you just find out what is the sub-shell for this 3 quantum number. You probably don't have to use this number ML. This ML just tell you one of those particular shape. Right? Again, a shape can be the dumbbell. So if you have different ML, that tell you have different this. You still have the same shape, whether it's stand up or lay down. So what is this? What is this standing for? What is this standing for? N is 3, L is 1. Alright, 3 something. 3 what? 3 question. Right. What is this? What's on for this pattern? How many d-type? How many orbitals in d-type? In 5D or 4D or 3D? So you have a D. You don't have a 2D. So that's 5. Okay. So what quantum number, if I give you a few sets, which is not good? Which is not good? Remember, let me remind you of this relation. N can be any number 1, 2, 3, something like that, right? They are all connected. Okay, so so in all those, I give you some number for n. Usually you will go by, if I give you n, what is the possible n for L, right? L can be what? 0 and n minus 1. ML can be negative L, 0, and L. Very good. Why D is not good? Yeah.
What is it?
D. Yeah. D, the color, there are few we can change, right? If you think about this, n is okay, right? N 4 is okay. Right? So if n is 4, right? And obviously this L is okay, right? And if L is 1, the only possible number for this is the negative 1, 0, and 1. Right? I think you'll be able to find that out. Which of this is the same as the example, which of this is not good? C? E? Why?
You started with the sport.
This is N is 3, and your L is 3. Not good, right? L, remember L can only be 0. Not all the same time, just 0, just like you just see all the possible numbers of n minus 1. So then the other thing we get from the quantum mechanics model is that E, energy. Right? This last area is about how you use this result. That result can have a very simple formula from the H atom to some calculations. Right? Most of the time you will feel a little difficult to do the calculations, but a few times you also confused about whether you release a light or whether you absorb a light, whether you release a photon or absorb a photon. I just know like from this simple Gauss model, so this is not reality, but this gives us some idea to make the calculations, right? So this Gauss model tells you for the H like atom, for the hydrogen H atom, there are no details n, no detail for 2, no 2s and 2p as what I saw there before, right? So everything like has n3 is the same because they have the same energy. So for us, for this session, just try to understand what we mean by absorbing energy and what we mean by release energy. Okay? So here, when the n is 1, it's closer to this dot, which is nuclear, and the energy is low, it's kind of deep inside in a hole, in a well. Okay? You can think about this is our E energy well, like a well to get water from. Okay? So when the n getting larger, and the water getting like more and more, and closer to the top. Right? So you can see those red arrows, tell you like those lines come from like this one. What that means is that when you have the electron here, and in this N3, so here's N3, and that is not usual, because usually they will be in a lower place. You will fall back, so go back. When they go back to 2, they will give you this red line, and you can measure that from this red line here. Okay. So that tells us also when the electron is from a higher energy state, go to a lower energy state, it is emitting the light. Obviously, right, if your electron starting on the 2, and somehow emitting electron go to the 3, it will absorbing those kind of wavelengths called the red light. Right. So that this model, the Gauss model, And the quantum model for the H atom, both of them give us a very good equation to do the calculations. This again is what I said, you should understand what the process will release light, release energy. So this process from lower to higher, you absorb, the electron absorb energy. You go from higher to lower, it will release energy, maybe at different radiations. So sometimes will release as UV light, sometimes maybe infrared. In the lower, not really that much infrared. Infrared usually emitted from those vibrations. So for the hydrogen atom, it's really an interesting process practice. And so the top line is absorption. You see the bright rainbow background, okay? And then you have this few lines that was taken out is because of some of those electrons in the lower state and come out to a higher state, absorbing those energy from the spectrum. And this is a darker background that has a few bright lines, which means those few bright lines will come from those electrons in the atom from higher to lower. What is interesting is we will do the lab, measure those, we can measure those results pretty much matching like those calculations. So how you do the calculation? You just kind of use like what we learned in the last chapter. We can think about the light is one part, is maybe the system, the atom is the other part. So you have those energy interconversion, right? So all those emitted light or absorbed light get into the electrons. The emitted light come from the electrons. You can find out the difference between the final energy for the electron, the initial energy for the electron, right? So as usual, what we did in chapter 6, you want to find out the energy change. So this delta E is an energy change for the electron. And as you learned in chapter 6, any change for the final minus initial. What we did for in chapter 6, right? Now you have a particular formula you can calculate or you can apply to those guys. But before we do that, or either way you can do this one first or that one first. We do the conversions. We know if the electron lost energy, and then you will produce those photons, which means you emitting the light. So vice versa, if there's some photon that disappeared, which means it was absorbed by the electron gain energies. So how much the electron gain or loss will equals those photons emitted. I think in the first few sections you learn how to calculate. If I give you this number in the last few sections, and I just simply call that E photon, right? And you can calculate E photon if you know the energy, whether they are absorbed or emitted. And then the question is, how do you calculate those energy change for the atom? I think I deleted one equation. So that means this number, I will put here, this number, so in general, it will depend on this equation. So equals negative 2.18 times 18 times J1/n squared. So that's the equation you saw that in the last few slides. It's a very simple equation. This is just a huge negative number. You take the negative number divided by n squared. So therefore, if you tell me what is your n, you just put in this equation right away, you will find out this number. Initial, that means you have an initial n. Final means you have a final n. Got that? Right. And if you put all those together, you get this equation, which is very, very straightforward. So here, this negative here is still here, right? Now this part, because this negative already here, now this delta E, or in this larger bracket. The larger bracket would mean this number minus this number. Now this number will become this part in the first middle bracket. Okay, so you still have this huge negative number divided by n squared, n1 squared. If it's final, it's n final squared. And then this second one is from this, and that's the same as this formula. You kind of accumulate. Okay? So you take this huge number divided by n squared, n1 squared, n initial squared. Right? So then once you have this equation, you can just substitute this by what you learned in the first few seconds. You know that E photon, this part is HC over lambda. If you don't want, you can just use H times mu equal to that. Right? So depending on what you want to find out, quicker. If you just want to find out what is lambda, just forget about that. Just say H over lambda equal to this. Okay? Right. So this again, this show you like those emitting process. So all those few arrows here, you draw like from higher to lower. If you have the arrow going from higher to lower, which means you're emitting energy out. That makes sense? Emitting energy out, that means you will do the calculation, your energy delta E is negative. That's very similar to what we talked about in chapter 6. Right? Because here is a more negative number, and there is a less negative number. And use our value to find out the result is a negative number. Right, so then you have different those. If you go from there to there, those give you the so-called ultraviolet UV light. If you go from some higher level, not all the way to 1, you go back to 2, and you will get those visible wavelengths. Visible wavelengths, which means visible light has different like less energy than UV light. You can see that more energy because there's a lot of gap. Less energy, the visible light is all adding up onto the second level. And if you go like even like less, you go like only to the 3. So there's a few in infrared. Right. So you want to determine the wavelengths of light emitted when this one from 6 to 5, right? Make sure that's not right. I mean that's right. You go from 6 to 5, you go from higher to lower, so your energy will be emitted. And so what you use, you can just use that HC divided by lambda, right? That equals negative. Another one, and then negative 2.18 times negative 18, 1 over. I will just put that n squared, then you tell me what n shall we use, right? And then this n final, right? And then other one, this one you can put in a bracket because it's a negative number, right? The other one with similar negative number, negative 18, 1 over, this one should be n1 squared, n initial. Right, so then the process will be very simple. And these two numbers multiply. Anyone try to remember what I tell someone? I tell like magic Tuesday, try to remember what is the number H times C. 1.9878 times 10 to the negative 25 over lambda. And this 9878 is two particular year, 98 and 78. Equals negative. Alright, so now you just substitute those numbers. What is our NF? 5 squared. Now here, I will just write plus. Where does the plus come from? Minus negative. And this 6 squared. What do you think? You'll get a positive number or a negative number for the lambda?
Lab time.
Positive number.
Please do lab.
Just,
Well, we're gonna three of them.
There's
There are
three.
only 3 guys.
Only three.
how we can do that? My group, do I? Another group, you want to do all the 3?
No.
No.
Don't we have to find the inverse or something for a photon from an atom, right?
You want to find out the negative?
You have to flip it because.
Yeah, that's what we figured out here. Yeah.
Alright. So.
Here, I think this is what we flip. Here, I think this is a different way, so from the book. We first use this equation, these 2 equations combined together, right? That's usual, that is the delta E, delta something from capital 6, right? And always like the, always the final amount.
Volleyball happened.
Right. Does that make sense? Does signify that the delta E is negative, right?
Countless times. I was in jam.
See that, delta is negative, right? So that's the emitting, right? Emitting energy is negative, kind of like an exothermic process. Now you switch, Mike can see that, right? So you get the delta E for the atom or for the electron, now your E photon is negative of those delta E atoms, and then you have positive. So now and once we have the positive, once we have that E, then you can just use either equation, HC divided by lambda or the H times U. So I think what I showed you on the last slide is like put everything together. So that probably, that's really good time. Okay, so what do you do? This is about electron transition. From 3 to 5, if you use like because that is the same process of the last slide, you will get a negative lambda, which means that for the photon, for the light, it was absorbed by the atom. So do a priorities, and you can use that formula, my formula. If you want, I can write it out here, so that's equal to this. Right. So if you use this equation in calculate, you will like see a few steps, right? And then you can memorize this equation. So if you have this equation in calculate, you will get a positive number. Positive number, which means you emit a photon.
What?
This calculation about photon as our system. Right. So now.
Why did you add them instead of subtracting?
Because it's final minus initial, and they're both.
This comes from the final and the initial for the delta H atom. And once you put those delta E atom equals E F minus E I. Then you also have that conversion, so delta E atom equals negative E photon. Then you just write negative delta E atom, what about the negative here? So we'll keep writing the negative on the outside. Okay? E cross negative HC divided by lambda. Right? Now you can multiply negative one here, then negative one here. So this kind of gives us that equation. I think that's very good question. You don't want to like memorize so many, just memorize some of those very basic equations, then you will get this equation if you on the exam. There's some number? E? And you get E?
Yes.
Very good. You probably get, if you use this equation, you will get a negative 1280. But as I said, you get a negative, that means the photon like this is here. I think that's the last one, right?
Yeah, that's not.
This is the last one. Yeah, so what you do, just use. Try to use that one again. Try to use this equation. So I will tell you that equation. Find the principal of the level 2. So let's start from this one again. H divided by lambda. And that will equal negative. If you want to memorize, you can memorize this equation. And the next step, you know this to multiply the line from 9, 8, 7, 8 times 25. What? Divided by lambda.
Sorry.
Negative 2.18 times 10 to the negative 18.
Don't take it personally.
What is our NF? Do we know NF?
Hey, don't blame the victim.
We'll keep this as X. And then this will be 2.18
All
times
lines in
18. What are our initial? So you can see that will be 36. Right?
Is it A?
The answer is 1, A. Now before you finish this, you just have to change this into like a meter, right? So this becomes 93.8 times 10 to the negative 9 meter. What you do, you will put this number here, 93.8 times 10 to the negative 9, right? This, I think one have this, that will be, here probably a bracket, so have a bracket. So here is the bracket. So you know every number is have this number. If I just get a number, then this becomes negative, move over become positive. So this number, this number,
Wait,
equal to this. This also becomes positive.
It's Stanford Technology?
No. Like, last week's math?
Yeah.
They give like 45 minutes for it.
Yeah.
So, like, Stanford University obviously did the same math for like biochemistry or whatever.
Yeah.
They split it up into 2 different days. The actual, like, whole thing.
I'm really sorry. That's on camera, that's great.
No, get your saint out of here. Sand.
Yeah.
Yes. What?
Hey, wait, which slide were you guys doing?
Because three groups, right?
So you didn't know that?
Well, this group is three groups, there's three lines, right?
I think we need to
Maybe, you know, this is never big like about, few minutes. Become the block, then in middle school you have to go through the line number. So this is the development, that's X. Right? Yeah, that looks good. So we measure, I think our conclusion is more than like 1/7, C divided by 1, 26, 18. Yeah. That's okay, that's okay. I think already what we claim is 18, but the usually probably won't be put even more, because, you know, this, the consumer said, you said it's 20%, and if something measure not 100%.
Turn on each other.
No, you might not have to hear you.
I wanted to let you know that I forgot my story at home and
Yeah.
I bring it to you on Tuesday.
Yeah.
No points because you're not here, so.
Okay, so I will not,
Did that point that I'm here. Okay, thank you.
welcome.
We have the keys.
Yeah, so
So do we have to do all three, or just
We
pick
choose.
one?
we can choose one, let's see if we have time. I think those two levels relatively easy. You can start from one, if you finish early, you can just second.
Just start a second one?
Yeah.
Okay.
Maybe everyone starting from different ones. So.
Okay.